Imagine looking at two massive, like highly complex manufacturing plants.
Right. Just totally different setups.
Yeah, exactly. On the surface, they operate by completely different laws of physics. Like one plant is a generative model, right? It takes pure chaotic noise and maps it down into high fidelity pixels.
And then the other plant is a vision encoder.
Exactly. Taking complex, high-resolution images and compressing them into dense semantic vectors. So you have these two completely different factories with totally different blueprints producing totally different products.
But then you look under the hood.
Right. You look under the hood and realize that mathematically, these two different systems are inextricably building the exact same foundational component.
Which is, I mean, it completely shatters the way we categorize these architectures. For years now, we've treated, generative diffusion networks and contrastive vision models as advancing on parallel but totally separate tracks.
Because they're optimized for entirely different objective functions.
Exactly. So finding a shared latent geometry between them isn't just like an interesting quirk. It's a structural paradigm shift in our understanding of neural representations.
And that's exactly what we are tackling today. Welcome to this deep dive. Now, since you, our listener, already have a serious background in machine learning and data science, we're going to go ahead and skip the introductory definitions today.
Yeah, you already know how stable diffusion denoises latents.
Right, and you know how models like CLIP and Dino map semantic embeddings? So our mission right now is to rigorously deconstruct a pretty groundbreaking paper from researchers at Technon. It's titled The Universal Normal Embedding, or UNE.
And we really want to figure out how these completely divergent AI architectures ended up discovering the exact same geometry.
Yeah, and how we can use that mathematical discovery to completely bypass prompt engineering for image editing down the line.
So to really get at the core of this, I think we need to start with the theoretical framework the researchers used to bridge synthesis and representation.
Right, setting the stage.
Yeah, they're building on a concept known as the Platonic representation hypothesis.
Which is such a cool name.
It is.
Yeah.
And the general idea there is that as AI models get larger and train on more and more data, they naturally converge toward a shared, optimal, latent description of reality.
A universal truth, basically.
Sort of, yeah. But this paper takes that really abstract idea and gives it a highly specific geometric structure.
Right. They formalize this ideal structure as the Universal Normal Embedding. And conceptually, the UNE is posited as a perfect, multivariate standard Gaussian latent space.
Which, mathematically speaking, we're talking about a normal distribution centered at 0 with an identity covariance matrix.
Operating in some incredibly high unknown dimensionality, right?
Yeah.
And in this perfect space, linear directions perfectly align with human semantics. So like a straight line through this space equals a single isolated human concept.
But the critical realization in the paper is that actual deployed models don't achieve this perfect ideal.
No model is perfect.
Right. The theoretical UNE is pristine, but what a given model actually learns is termed an induced normal embedding, or IEN. And the relationship between the true UNE and a model's learned IEN is strictly linear.
Meaning what, exactly, in terms of the math?
Well, for any specific model, its latent space is basically just a linear transformation of that perfect universal normal embedding, plus some model-specific architectural noise.
Okay, let's unpack this for a second. If we think about the true UN as this massively high-dimensional geometric object, say, like a perfect glowing multidimensional sphere, then our individual models, whether that's Stable Diffusion 1.5 or Diame 3, are essentially just differently calibrated, slightly noisy sensors.
Yep, like that. Noisy sensors.
Right. Each sensor is looking at that exact same multidimensional sphere, but only capturing a lower dimensional linear shadow of it.
And the specific projection angle depends on the model's architecture.
Yeah, and the fuzziness of the shadow is the model-specific redundancy.
That's a great way to visualize the matrix operations happening here. The induced normal embeddings preserve the core, linearly separable structure of that master shape.
Even if a specific model discards certain dimensions.
Exactly, or injects its own noise. The geometry survives the projection.
But I've got to push back on this a little bit because mechanically it seems highly counterintuitive.
How so?
Well, we know diffusion models are explicitly trained to map to a Gaussian prior. That's the entire bedrock of the forward and reverse diffusion process.
Right, the diffusion mechanism demands it.
But contrastive foundation models, though, things like CLIP or OpenCLIP, are not bound by explicit normality constraints.
They're really not.
They use InfoNC or similar contrastive losses to push positive pairs together and negative pairs apart. So why on earth would a contrastive model naturally converge to this exact same Gaussian geometry?
What's fascinating here is that this convergence is entirely driven by the implicit pressures of self-supervised learning. You don't actually need a hard-coded Gaussian prior.
Wait, really?
Yeah. Contrastive learning relies heavily on spreading features uniformly across a hypersphere to maximize the distance between negative samples.
Oh, I see. To keep things as distinct as possible.
Exactly. And on top of that, these architectures utilize redundancy reduction techniques that actively work to decorrelate features.
Right.
So when you force high-dimensional features to decorrelate and spread uniformly across a spherical space, the mathematical byproduct, almost inevitably, is an embedding space that pushes toward a smooth, Gaussian-like distribution.
So it's not a constraint, it's an emergent property of the optimization landscape itself.
Exactly. It just happens naturally.
That makes sense in theory, but proving that these massively complex, nonlinear latent spaces actually behave as perfect Gaussians requires some serious statistical heavy lifting. I mean, you can't just eyeball a 10,000 dimensional space.
You certainly can't. And that's why the empirical validation in this paper is so incredibly rigorous.
Yeah.
The researchers basically threw a brutal gauntlet of statistical normality tests at these latent spaces.
Which tests are we talking about here?
Tests like Anderson-Darling, D'Agostino-Pearson, and Shapiro-Wilk.
The classics.
Yeah, but they didn't just test a handful of cherry-picked vectors. They evaluated thousands of random, one-dimensional projections across a whole suite of models.
Right. They looked at Stable Diffusion 1.5, Stable Diffusion 2.1, LCM, CIP, OpenCLIP, and Dino v3.
And testing for normality in spaces with that many dimensions usually completely breaks down.
Oh, yeah, because of cursive dimensionality artifacts. Most distributions just fail those tests instantly.
They do. But the results here were staggering. The generative models practically hit the theoretical maximum. They approached a 95% acceptance rate for Gaussian samples.
Wow.
Yeah, that is near perfect adherence to the Gaussian ideal. And the encoders, which again have zero explicit normality constraints in their loss functions, scored just slightly lower.
It's still really high, right?
Oh, highly Gaussian. Acceptance rates were hovering between 88% and 92%.
That is wild.
And they even ran these same tests against non-Gaussian reference distributions like bimodal Gaussians and uniform distributions, just to be sure.
And I'm guessing those failed.
Catastrophically.
Yeah.
The data makes it undeniable. Both generators and encoders are operating in a distinctly normal geometry.
And the reason we care about proving it's a Gaussian geometry is because it mathematically guarantees certain functional properties.
It unlocks the math.
Specifically, if the latent space is standard normal, and we assume that semantic attributes like a person's age or the lighting in a room are jointly Gaussian with the latent code, then we trigger the linear expectation property.
Yes. The closed-form conditional expectation of a multivariate Gaussian is a beautiful thing.
It really simplifies things.
It does. It dictates that if a latent code and a semantic attribute are jointly Gaussian, their relationship is strictly linear.
Meaning what, practically?
This means that a complex semantic variation in a highly nonlinear model actually corresponds to moving along a perfectly straight line, just a simple vector, in the latent space.
Here's where it gets really interesting. To test this linear separability in the real world, the researchers ran an experiment using the Celeba validation set.
The facial attributes data set.
Right. They trained simple, lightweight, logistic regression linear probes on 40 different semantic attributes. Things like smiling, or wearing lipstick, or receding hairline.
It's just basic binary classifiers, essentially.
Exactly. And they applied these linear probes to the latent representations of both the encoders and the generative models.
And the revelation from those probes is the absolute performance parity between the two paradigms.
They matched.
Completely.
Yeah.
They took raw spatial diffusion noise from Stable Diffusion 1.5 specifically, the noise inverted via DDIM, the denoising diffusion implicit models process,
Yeah.
and ran these linear probes on it.
Okay.
The attribute classification accuracies on that raw noise were nearly identical to the classification accuracies achieved in the latent space of CLIP VIT B16.
Wait, we really need to let that sink in for a second. Raw, DDIM inverted spatial noise from a diffusion model holds the exact same linearly separable semantic structure as a text image encoder.
Yep.
An encoder that was explicitly, purposefully trained to recognize those exact semantics.
It's crazy.
The diffusion model didn't just learn a neat trick to denoise pixels. Its noise space naturally organized itself into a highly interpretable linear semantic coordinate system.
It forces us to completely reframe how we view generative noise. It isn't just some random seed used to kick off the synthesis process. It's a highly structured semantic embedding in its own right.
Which has huge implications.
Massive. From an engineering perspective, if diffusion noise is semantically organized and linearly separable, practitioners can exploit that for incredibly granular, controlled image generation.
Completely bypassing the need for complex prompt engineering.
Exactly. Or heavy architectural modifications like
Yeah.
ControlNet. You just do math in the latent space.
Okay, so if the noise is structurally identical to an encoder's latent space, how do we exploit that in practice? Like if I'm an engineer staring at a terminal, how do I actually manipulate an image using this geometry?
The mechanics in this Gaussian space turn out to be incredibly straightforward.
Walk me through it.
To edit an image, you just take your original DDIM inverted latent code and you add a specific semantic vector to it, scaled by however intense you want the edit to be.
So that's the core vector addition.
Yeah, you find the normal of the learned linear decision boundary for a specific attribute, say the vector that points directly toward the smiling classification.
Right.
You scale it, add it to your noise, and then run the standard denoising process. The resulting image comes out smiling.
But doing that introduces a classic machine learning entanglement problem.
Oh, absolutely.
Because attributes in real-world datasets, especially faces, are heavily correlated. If I find the vector for adding a goatee and I just blindly move my latent code along that vector, I might unintentionally alter the subject's entire jawline or facial structure.
Right, because the model learned those features together in the training data. Goatees and masculine jawlines co-occur frequently.
Exactly. So how do they mathematically prevent this kind of spurious feature entanglement?
They solve it with a very clean application of basic linear algebra, specifically orthogonalization.
Okay, break that down.
To isolate the target attribute, you project your target direction into the null space of the spurious direction.
Null space projection.
Yeah, but let's step away from the raw formulas and just visualize the vectors. Imagine you have an arrow in this high-dimensional space pointing toward goatee, and another arrow pointing toward the underlying jawline shape you want to protect.
Right, because right now, moving along the goatee arrow slightly pulls you along the jawline arrow too.
Exactly, they're not at right angles. So you mathematically compute the projection of your goatee vector onto your jawline vector.
Which tells you exactly how much jawline influence is contaminating your goatee edit.
Bingo. You then subtract that projection from your original goatee vector. What you're left with is a corrected, purely orthogonal direction.
Oh, wow.
Yeah, it's a vector that adds a goatee while having absolutely zero mathematical alignment with the jawline. You get clean, isolated edits without touching correlated attributes.
And it's crucial we highlight a major comparative detail from the paper regarding where you actually perform this linear editing.
This is a huge point.
Right, because if you do this orthogonal vector addition directly in the stable diffusion latent space and decode it, you perfectly preserve the original image structure.
Pixel perfect.
It's the exact same subject, the exact same background, just modified with a goatee. But what happens if you try this exact same linear edit in COIP's latent space?
Well, that's where the architectural differences still matter.
Yeah.
COIP's latent space is fantastic for representation, but it's not directly invertible back to the pixel domain.
You can't just decode CLIP.
Right. To turn a modified CLIP vector back into an image, you have to use a translation tool, like an unclip model. And when you do that, the output perfectly matches the new attribute you added, but it generates an entirely new image from scratch.
You completely lose the original subject.
Exactly. This proves why finding this semantic linearity natively inside the diffusion noise space is so powerful. It gives you the semantic control of an encoder, combined with the pixel-perfect faithfulness of a generator.
And just to prove this isn't some weird artifact limited to data sets of human faces, the researchers tested this generalization using the AFHQ dataset.
The animal faces high-quality set.
Yeah. They successfully applied this exact same orthogonal editing technique to transform cat features into dog features along a single linear vector. So the linearity holds up across entirely different visual domains.
Which logically leads us to the final and arguably most mathematically ambitious phase of their research.
The big unification.
Exactly. We've empirically proven that these diverse models share Gaussian geometry and linear semantics. We know they behave the same way. The ultimate challenge is, can we mathematically translate between these spaces?
Can we map one to the other directly?
Right. Can we isolate the pure shared intersection of all these different latent spaces?
Well, to even allow the community to test this, the researchers had to build a massive new resource called the Noise Zoo dataset.
A huge contribution to open science.
Absolutely. Noise Zoo contains the per-image D-dim inverted diffusion noise paired with the matching encoder representations for roughly 19,000 images from the Celeba validation set.
So you have the ground truth for everything.
It literally gives you the exact latent coordinates for the exact same image across Stable Diffusion, LCM, CLIP, and Dino.
And having that paired data is what makes cross-space transfer possible. Using the Noise Zoo dataset, they first tested basic linear mapping.
Just simple regression?
Exactly. They used ridge regression to translate Stable Diffusion noise latents directly into CLIP and Dino latent spaces.
Did they regularize it?
They did. To ensure the mapping was stable, they scaled the ridge penalty by the energy of the source features, which keeps the translated vectors really robust.
And the downstream effect of just sliding from one model's brain into another's using basic regression.
Near zero degradation.
Right, really?
Yeah. When they took these linearly translated latents and used them to predict attributes, the accuracy dropped by less than 0.3 percentage points compared to using the model's native latents.
That is absurd.
It emphatically proves that you only need a simple linear matrix multiplication to perfectly align generative noise with a contrastive encoder space. The spaces are geometrically analogous.
But the crowning mathematical achievement of this paper goes way beyond just mapping Model A to Model B. They wanted to find the universal normal embedding itself.
A holy grail.
Or at least that they wanted to extract the shared core subspace that every single one of these models agrees on. And to do that, they utilize the Maxiver formulation of generalized canonical correlation analysis.
GCCA.
Right, GCCA.
And GCCA is a beautiful application of multi-view learning. Imagine we have 5 or 6 different models, each providing a different view of the same image.
Like different cameras pointing at the same object?
Precisely. We want to find a single shared core representation. Let's conceptualize it as a central matrix that every single model can linearly map to with minimal error. The Maxiver objective function minimizes the difference between the model's projected latents and this shared central matrix.
But they don't just let the optimization run wild, right? They enforce specific geometric constraints on this central matrix to force it to behave like the theoretical universal normal embedding we talked about at the beginning.
That's the key to making it work. They apply strict centering and identity covariance constraints to the matrix.
Meaning the data has to be zero, mean, and decorrelated.
Exactly. Perfectly decorrelated. By optimizing this closed-form solution via eigendecomposition, they successfully recover these shared core latent subspaces.
Which represents the mathematical consensus of the model.
Yeah.
So what does this all mean, like, practically speaking? The paper charts the linear probe classification accuracy against the dimensionality of this shared subspace.
And the curve is really surprising.
It is, because even when they restrict this shared core to just 16 dimensions, the classification accuracy on complex human attributes remains astonishingly high.
16 dimensions.
I mean, think about the scale of compression happening there. You are taking the 16,000 dimensional noise of Stable Diffusion, the 768-dimensional space of CLIP, and the dense representation of Dino, and you are crunching their shared agreement down to a mere 16 variables.
That's a massive bottleneck.
So what does that imply about the intrinsic dimensionality of visual semantics?
Well, if we connect this to the bigger picture, it implies that the fundamental attributes humans use to define visual meaning, things like lighting, expression, geometry, age, are incredibly dense.
They don't need thousands of dimensions to exist.
Not at all. They concentrate in a remarkably small set of shared directions. The fact that the intersection of 6 radically different AI architectures yields such a potent 16-dimensional semantic core strongly suggests that these models are not just hallucinating arbitrary idiosyncratic features.
They're finding a real structure.
They're all mathematically discovering the exact same underlying low-dimensional manifold of human visual meaning.
Let's bring this all together. Today, we unpack the formalization of the Universal Normal Embedding. We examine the rigorous statistical gauntlet proving that generative DDIM noise and contrastive encoders share an approximately Gaussian geometry.
A really robust one, too.
We detailed how you can use orthogonal projection for linear semantic editing natively within noise space, preserving image fidelity while cleanly altering specific traits. And finally, we explored how GCCA extraction reveals a highly concentrated, shared semantic subspace across totally disparate models.
It really is a profound unification of representation learning and generative modeling. The mathematical frameworks that define how an AI understands an image and how an AI creates an image are no longer completely separate paradigms.
They're converging.
They are just differently calibrated, noisy, linear projections of the exact same underlying geometry.
Which leaves you with a final, lingering thought to mull over. We started by imagining two isolated factories producing the exact same foundational component.
Right.
If diverse AI architectures guided by entirely different loss functions, totally different training regimes, and different data modalities all naturally fall into the exact same low-dimensional Gaussian geometric subspace, are these neural networks actually learning unique representations of the world?
Or are we simply building different mathematical lenses, all focused on observing a fundamental universal coordinate system of visual perception that has always existed independently of the algorithms themselves?
Something to ponder. Until next time.